Section 4.1, Functions of Several Variables. In this chapter, we're going to work with multivariable functions. And first, we're going to start by talking about domain and range, graphs, traces and level curves, all for functions that can create 3D or other more complicated surfaces. We're going to start by talking about a function like f, which takes in two variables, x and y. And initially, you're going to struggle with the fact that y is now an independent variable. And that's because for the longest time, x was independent, y was dependent. But we're going to work past that. For this function, f, we know that we have two independent variables, x and y, and I can tell by the function notation f is the name of the function, x and y appear inside of the parentheses for function notation. So I know those are my independent variables. And I'm setting that function equal to the dependent variable z. So very similar to what we did in Calc 1, where you have y equals f of x, where we saw x was the independent, y was the dependent. Now we're letting y join the independent variable. So we need to create a new dependent variable, z. To graph a function like this, first we're going to picture the domain of the function. These are all of the combinations of x and y that the function can handle. So let's picture that domain as a section in the xy plane, like you see in this blue blob. Inside of that blob, I have all of the ordered pairs x, y that I'm allowed to plug into the function f. Each one of the points inside of that domain can be plugged into f, and it'll generate the dependent variable output z. That point that exists above the domain, or below in some cases, that's the function output. And if we generated enough points, we could create a surface above the domain or below. Here's a few different graphs of functions of two variables. Notice each function is equal to z, the dependent variable. And on the right-hand side of the equation, you can see the function of the variables x and y. Here you can see there's a lot of color going on in the graph, and that's really just to help give you more depth. The lighter color pink is saying that we are at a large value of z, and the yellow or orangey colors are saying that you're a small value of z. So it's giving you a gradient to map the color to the values of z. Let's refresh our memories of how domain and range can be described. For example, the function f of x, a single variable function, that's equal to the square root of x. We know that the domain is restricted to only non-negative values of x. And to graph that, we might draw a number line. We would say that starting at 0, including 0, and anything larger than that would be our domain, and we can graph that on that number line. The range would be any number that we could possibly expect to come out of the function. So ignoring what was plugged into the function and just saying what would you guess could come out. Mostly that's found by graphing the function and looking at vertical from the smallest value of y up to the largest value of y. So for this function, f of x, we can see the domain listed as an inequality is x greater than or equal to 0, and the range is listed as an interval, showing that we can expect all values of y between and including 0 up to infinity. Now I could have written the domain as an interval as well, starting at 0, going up to infinity. And I could have written the range as an inequality. Y needs to be greater than or equal to 0, less than or, we can't say equal to for infinity, so just less than infinity. So just to be clear, using this interval notation, we would write the domain 0 to infinity. Using the inequalities, we call that inequality notation. Similar words, they mean different things, and they represent the exact same thing. So we've got to make sure we get the two of those clear. Now let's take a look at a multiple variable function. In this case, the function name is g. It takes in the variables x and y. And the definition of the function says square root of 9 minus x squared minus y squared. Now, we're going to have to use some of our knowledge about functions. For example, we know that the argument, or the inside of the square root, we call that the argument of the square root, that needs to be greater than or equal to 0. If it's not, then the function will break. So what we're going to do is take that inside expression and find out what will keep that true. Now we can't solve this explicitly for x or explicitly for y and have the entire domain mapped out, but instead what we're going to do is try to make that equation or inequality look as close to something we recognize as possible. Play around with a little bit of algebra, see what we can do. If I add x squared and y squared to both sides of my inequality, I end up with 9 is greater than or equal to x squared plus y squared. Now if this were just an equal sign, we might recognize immediately that this looks like a circle. But remember, it's not just an equal sign, it's an inequality that includes the equals. So this is a circle, but also all of the points that would fill in the circle. So our domain is the circle in the xy plane with a radius of 3. And when we plug all of these points into our function, we generate this red dome that you see on the right side of the screen. We can see that at the edge of that domain, we have the smallest values of our function. And we can confirm that by picking a value on the edge of the domain, maybe this one, where x is equal to 3, y is equal to 0. If we were to plug that into our function, we would see the point on the red dome right here. We would label that as 3, 0, g of 3, 0. Plugging 3, 0 into our function, we would have the square root of 9 minus 0 squared minus 3 squared. 9 minus 3 squared is 0, so this turns out being the square root of 0, or 0. So that point is actually 3, 0, 0. That's the smallest z-value that we can see on this plot. Notice that the largest z-value would be at the top of the dome. That comes from plugging the point 0, 0 from the domain into the function. So that point on top would be like x equals 0, y equals 0, g with 0, 0 plugged in. And if we plug 0, 0 into g, we would get the square root of 9 minus 0 squared minus 0 squared, which just looks like the square root of 9, or 3. So g of 0, 0 is just 3. Looking at the z-values from the smallest to the largest, we can find the range. The range is going to go from 0 all the way up to 3, including both endpoints, because we found the points that exist on the small side and the large side. And for our domain, if we wanted to list that, we don't really have an option for listing that as an interval right now, so we're going to use inequality notation. We're just going to say that our domain consists of the points x squared plus y squared is less than or equal to 9. In words, we could say the disk centered at the origin with radius 3. Or we can just say this equation, or sorry, inequality that we found. And then for the range, because the range is only talking about the one dependent variable, we can list that as an interval if we'd like, or we could list it as inequality. Either one is fine. Let's take a look at another function, g, with two independent variables again, x and y. We're dealing with a square root function again, but the argument has changed. So this process will be a little similar, but we're going to get a different result. I'll take the argument of my square root and force it to be greater than or equal to 0 to find my domain. Working this inequality until it looks familiar, I end up with a circle centered at the origin with radius 4. This time, though, x and y are the points that are outside of the circle. And if I graph my domain, I can see that it's the entire xy plane with that disk cut out of it, which means that our function will only exist above this shaded portion of the xy plane. Above that disk in the center, nothing will exist there. And when we graph our function, we get this red surface. We can see that that's exactly what's going on, that we have a hole cut out in the center, and it more or less looks like a funnel that exists above the xy plane that's shaded in. So for our domain, we can use that inequality, x squared plus y squared greater than or equal to 4. And then for our range, notice that the smallest values of z appear right along this cutout circle in our domain. So we could pick a point that's right along that boundary, plug it into our function, and calculate. So we have here x is equal to 2, 0. I know it's 2 because our domain had that disk cut out with a radius 2. And y is 0 because we're on the x-axis. Plugging that into our function, g of 2, 0, we get the square root of 0 squared plus 0 squared minus 4. Oh, just kidding. X needed to be 2. So we get 4 minus 4 inside of our square root with an output of 0. So the smallest value of z is at 0. That point on our surface looks like 2, 0, 0. The largest value of z, well, to find that, let's think about the fact that we can extend in the x direction forever. That plane does not end. As x gets bigger and bigger, our inequality for the domain just gets more and more true, which means we can let x and y inside of our function grow without bound. And the square root of a number that grows without bound is also a number that grows without bound. So we can imagine that this funnel will extend indefinitely up in the z direction. So our range would be from 0, the lowest z value on our function, all the way up to infinity. Moving on to our next multivariable function. This one includes the natural log function. Now, in Calc 1, we talked about the natural log function. It's a graph that looks kind of like this. And we said that we couldn't plug in negative values for x, that the function does not exist for negative values of x. Therefore, we need to make sure that the argument of that function is not equal to 0 and not negative. So in this case, we need ln to be, the argument to be greater than 0, not greater than or equal to. So we'll take our argument, make a strict inequality here, and then we can try to make this as familiar as possible. We might have a habit of wanting to solve things for y, but in this case we get a more complete picture if we leave it in terms of y squared greater than or equal to x. When we graph that, we can see the parabola that comes from y squared equals x. And we're picking all of the y values that when we square them would be larger than x. So you get this shaded portion of the xy plane. If we plug any one of these points in our domain into our function, we get this red surface that we see on the right. Now notice that this red surface actually cuts through the xy plane about right here on this dotted line, but the domain stopped here. And that just means that these points are below the xy plane. So our function actually exists below the xy plane, and you can see that over here. So for this purpose, to find the range, what we need to do is think about what domain points are going to give us the smallest z value. And those are the points that would exist along this cutout parabola. So if I pick any one of these points, maybe the easiest point to pick would be the origin, x equals 0, y equals 0. But I could pick any other point along this parabola and plug it into our function to figure out the smallest value of z. If I tried to plug in x equals 0, y equals 0, notice that ln of 0, it's negative infinity. So g of x and y can go all the way down to negative infinity. And as far as how large it can get, we know that the natural log function continues up indefinitely, so we know that we can get all the way up to positive infinity as well. And for our domain, we'll just copy down that inequality, y squared needs to be greater than x. So with these few examples that we've seen, we should probably get the idea that finding domain and range is quite similar to how it was for a single variable function, except for that when you have multiple independent variables, your domain might include restrictions from any one of those variables or all of them. The output, however, will only depend on the single dependent variable. So even though we're having multivariable functions, the multi part really refers to the input variables. You can have multiple input variables, but you will only have a single output variable.